Okay, so problem 3 is where it starts getting, for lack of a better word, more interesting. In this case, I recommend that you break this up and use superposition. So I recommend that you look at this as one case, and this as another case. I didn't draw this to scale, but those are the two cases I would recommend you look at. And for this, I strongly encourage you to use your moment area theorem. So again, let's look back and think about what our moment area theorem is. Moment area is literally what it sounds like. It's the area of my moment diagram, and how do I use that to get interesting values. So if I think back to my, what is moment? Moment is just equal to the, or actually, what is my change in moment? Change in moment is really just equal to the area of my shear diagram between 2 points, right? Similarly, I can do the same thing with rotation. Right, these two have a very similar relationship. I integrated my shear diagram to get the change in moment. I'm integrating my moment to get the change in angle, change in rotation. This is my first moment area theorem. It basically says that the change in angle between A and B is equal to the area of the moment diagram between A and B. My third equation is this infamous TBA equation. That is just equal to the integral of mx on EI times dx. I forget there's a name for this in statistics. I can't remember what this is, but you can think of this as like taking the moment of your moment diagram. It's like basically multiplying. This becomes area of your moment diagram from A to B times the distance from the centroid to B. These two letters have a very special meaning. Do not mix them up. B, or the first letter, is always the point you're interested in. A is the point that you're drawing your tangent about. So for example, if I have a beam like this, where this is A, this is B, and this is C, my deflected shape, let's say I have some distributed load, right? My deflected shape would look something like this. This is the tangent at A. This is TBA. It's the distance from the tangent at A to the deflected shape at B. Distance from the tangent at A to the deflected shape at B. TAB would be this distance. This is TAB. It is the distance from the tangent at B, right? The tangent at B, if I'm assuming B is in the center and this is symmetrically loaded, then B is going to be 0. The tangent at B is going to be horizontal. It'll be 0 slope. The difference between distance from that point to the deflection at A. So whenever you see those two, make sure you get that. Make sure you're very careful with your notation. They do have a special meaning. With that, how do I actually solve this? The first step, again, I said to break this up into two pieces. The first step is to draw your moment diagram. And I think the easiest way to do this is to draw my shear diagram quickly. My shear diagram will just be this, right? It'll just be a triangle. Therefore, my moment diagram is going to be, if I draw my moment diagram going positive downwards, I'm going to end up with I start off with a negative value. It has a large positive slope, and something like this. this height here, this is length 4L, therefore this is going to be 4P. This is 4L. Area is 4P times 4L, 16PL divided by 2 because it's a triangle. It's going to be 8PL. That's the height of my moment diagram. Sorry, this is negative 8PL. That's the height of my moment diagram. I actually need to draw my M on EI diagram though, and this is where that 2EI and EI comes into play. I'm essentially going to divide this section by 2EI and this section by just EI. And what that means is that at this point I'm going to have a jump. My moment diagram is going to look like this. Oh, sorry, not my moment diagram. My M on EI diagram. Right, I'm taking negative 8PL here and dividing it by 2EI. Therefore, I'm going to get negative 4 on EI. Sorry, negative 4PL on EI. Down here, I'm going to take this value, and what is this value? Do you agree that if this whole thing is 4L, and this is L, then this is going to be P? P times L times 1/2. Right, I'm trying to get the area of this small triangle here, or the area of the moment diagram and just this, sorry, the height of the moment diagram at this point, where they change. Look at this. That is going to be PL on 2. PL on 2. I'm dividing that by 2EI here. This is going to be PL on 4EI. And this over here is going to be PL on 2EI. Right? Technically they should have the same value, but on the left side I'm dividing it by 2EI, on the right side I'm dividing it by EI. Therefore I end up with this extra 1/2 term in here. And this is where the jump comes from. And again, this is my M on EI diagram. Now, in order to analyze this, I have to look at this area, right? In order to find the deflection at point C, I need to find the area of this complicated shape and the centroid of this complicated shape. Instead of doing that, I'm going to break this up into 3 separate pieces and analyze each of those individually. And that'll, even though that sounds like a lot more work, it'll actually make things a lot easier because I'll have true parabolas. But what do I mean by true? I mean that the tangent at a point on the parabola is 0. So I look at this. Do you agree that I can draw this as one big parabola? I can add in I can look at this small parabola here as well. And then I can look at the big, or I guess the medium parabola out here. So let me just draw the heights in here. This height here is negative 4PL on EI. This height here is negative PL on 4EI. This height here is PL on 2EI. I'm going to, this section here is essentially double counted. Right? I'm going to pretend that this parabola isn't cut off. I'm going to look at the whole thing. I'm going to look at this green parabola in here. And then I'm going to subtract off this small section of the first parabola, which I'm double counting right now. So when I go through this, I'm going to take this section. Let's call this 1. Let's call this 2. Call this 3. I'm going to take 1 minus 2 plus 3. And that'll be my deflection at C. I'm going to find one of those values right now. What is the deflection at C due to this big parabola up here? That is really just, so if I look at delta 1, for example, that is just equal to the height of the parabola. Or this is going to be equal to my TCA equation. that is equal to the area of the moment diagram, the area of this parabola, times the distance from the centroid to the end. So that is equal to the height of the parabola is negative 4pl on EI. The base of the parabola is 4L. The area coefficient, so the coefficient for a triangle is 1/2. The coefficient for parabola, for this type of parabola, is 1/3. 1/3. The distance to the centroid. The centroid of this kind of parabola is here. That is 1/4 away from the base. Sorry, 1/4 of the base away from the tall edge. So in other words, the distance from here to the point that I'm interested in is 3L. It is 3/4 of 4L. 3/4 of 4L. And I think that is everything for that first part. Right? This is you can think of this as my height. This is my base. This is my area. And this is my centroid distance, x bar. Similarly for delta 2, I'm going to look at TCA. And I'm going to do the same thing, except some of these values are different, right? My height is now negative PL on 4EI. My base is now L. My centroid distance is 3/4 times L, not 3/4 times 4L. So those things will all change. I'm going to do that for delta 2, delta 3. I'm going to add all those together, and that is delta C do, so delta 1 plus delta 2 plus delta 3 is equal to delta C due to distributed load. I also need to, so once I have this, I need to find the deflection at C due to this arbitrary load, By. I'm going to draw my thing again, my diagram, but just for By in this case. My moment diagram for this is just going to be a triangle. Right? My shear diagram is like this. My moment diagram is like this. The height of this is going to be, sorry, this is negative By here. The height of this is negative Byl, or sorry, positive Byl. So I have this. I'm interested in the deflection at this point, and it is okay for me to use moment area for a portion of my diagram of which I do not. What am I trying to say here? I'm trying to say that even though I'm interested in this point and the diagram doesn't extend all the way out to this point, I can still take the centroid times this distance. That is fine. So I want to use my delta By. I'm going to say my delta at C4, and this is due to the point load By, is going to be equal to this area divided by 2EI, right? Just divide this by 2EI times this distance. For a triangle, this length, this triangle is 3L. This length is L. Centroid distance is going to be 3L. This length here is going to be 3L. I had to split this up into two parts, so I'm going to just stop this here. I'm going to continue this again in just a sec, so just go to the next video.